Okay, numbers. So we'll start with numbers as we understand them as human beings. So we have a set of symbols to describe the numbers when we're referring to numbers. Okay, and the symbols that we use are the following ones, which I'm sure you're familiar with these already. Okay, so these are the symbols that we use to represent the decimal number system. Who invented these symbols, by the way? Or where does the idea of having 10 symbols for numbers come from? Anybody know? Yeah, it comes, I think, from the Arabs originally, but I think the Arabs actually got it from India, so I think it goes back, thousands of years, and I'm not quite sure where it originates, but I think it was India. Anyway, we have these 10 numbers, okay? And once we reach 9, what do we do? Double digits. We use this positional system here, okay? So this is what we call a positional number system. Now, positional number systems, there are other number systems which are non-positional number systems. Can anyone give me an example of a non-positional number system? Roman numerals are non-positional. So in other words, the position of where things occur in Roman numerals does not tell you anything about the number. Whereas the position here in this decimal number system tells you something significant about the number system. So the first thing that we can know about these numbers is we count. And once we're finished counting and once we run out of symbols, what do? You start counting again, but you move over one thing on the left. And you put a 1 in here, and then you start counting again. 0, 1, 2, 3, 4 here, and then you put a 1 over here. This 1 tells us something significant about this number here, this 1 and the 10 here. What does the 1 here mean? What's the significance of the fact that it's moved over by one space? What does that tell you about the number? Sure thing. But the fact that this 1 here, that doesn't mean 1. It doesn't mean 1, it means 10, obviously. I mean, this number here, if I was to pick this number, say that's 10, and then we have 11, and then we have 12 here. In that number there, that 1 doesn't mean 1. What does it mean?
10 plus 1.
It means 10 plus 2. Alright, if I take this number here, 128, this 2 here means what? 20. This 1 here means 100. So this number, we could break it down to saying that's the number 100 plus the number 20 plus the number 8. Okay, that's positional number systems. Now, interestingly, when we're looking at these positional number systems, right, again, let's pick the number 128 here. This is the ones column, isn't it? This is going to be the tens column, and this is going to be the 100s column, like that. All right. Everybody happy with that? So, computers, on the other hand, use a different system for representing numbers. And in fact, computers don't really work with numbers at all. Even though we think, wow, computers are great at dealing with numbers, they don't deal with numbers at all. What do computers actually work with at a very fundamental low level? Switches. They look with transistors is what they're all about. Transistors are combined together to make what? On and off switches. Alright? So inside your computer are billions and billions and billions of on and off switches. And RAM is composed of lots of on and off switches. Your CPU, which is the thing that actually does all of the calculations, is composed of lots of on and off switches called registers. And things get taken out of the RAM, put into the registers, added, subtracted, multiplied, and divided, whatever, and then sent back out into the computer's memory. Okay? So, in order to represent these type of numbers in a system which can only work with switches, which can either be on or off, we need a different type of numbering system. And the type of numbering system that computers use in order to enable us to manipulate this stuff, using on and off switches, we use a system called binary. Right? So binary numbers are just numbers that use exactly the same rules as we're familiar with for decimal numbers, but they only use the digits 0 and 1. So when the switch is off, OFF, we say that that's a 1. And when the switch is, that's a 0. And when the switch is on, we say that that switch is a 1. So I'm just going to make a couple of little notes here as well. So the memory of your computer consists of lots and lots and lots of on and off switches. Okay, so those on and off switches, there's billions of them. I'll just make that note. billions of them. Okay, and in fact you can figure out exactly how many of these on and off switches are in your computer because you just look up and see how much RAM is in your computer. So say for example my computer had 8 gigabytes of RAM, 8 GB of RAM. Exactly how many switches are in 8 gigabytes? Do you know? Huh? A billion. A megabyte is, oh yeah, megabyte. Well, let's work it out, right? So, to represent these switches, when we group them together, we have names for when we group them together. The first grouping of switches is called a byte. And a byte consists of how many switches? A byte is exactly 8 switches, right? So you should write these terms down. 8SWYTCHES. A byte is usually the smallest thing that you can actually get access to in the computer's memory in order to program it or read a value from it. But you can use certain tricks to be able to read the individual switches. The individual switches, actually we'll write this down here, are called bits. So bits is basically one switch. A byte is 8 switches. You do have this other thing which I mentioned before, and 8-bit computers use them, and it's basically half of a byte, and it's called a nibble. You laugh now, but you know, nibbles, that's just the word. I didn't make it up, but when you think about it, you know, if you've got a byte, a nibble is a good name to call it. So a nibble is exactly 4 switches. Yeah. The point is, bytes are grouped into 2 nibbles, or 8 bits. And we don't really, you can't actually address any smaller than a byte without using some techniques like bit masking. Anyway, so that's a byte. So then we group these bytes together into groups of, they're always powers of 2, right? So you group a number of them together and you get a kilobyte. So how many bytes are in a kilobyte? There's 1024. And the reason why it's 1024 as opposed to 1000 is because it's a power of 2. These switches can be on or off, you know, so there's basically 2 settings for 0 or 1. And so everything kind of builds up from that kind of idea of 0 and 1, okay? So a kilobyte is 1024 bytes.
That's 1 gigabyte, isn't it?
No, we'll work up to a gigabyte, right? A kilobyte is 1024 bytes. Next one up from a kilobyte, we have what's called a megabyte. So how many kilobytes are in a megabyte?
1024.
Yeah, so this is 1024 kilobytes. Alright, it's also 1024 multiplied by 1024. So if you want to look at this in terms of zeros, it's 1000000. So it's a million, roughly a million kilobytes, or roughly a million bytes, right? I'll say 1 M bytes.
I think it's a 1,084,000, something like that. It slightly grows.
I'll actually just work the number out. It's very simple to calculate. Just use the calculator on the phone here. I should know this. 1024 multiplied by 1024. Delete 1024. So it's 104857. Okay, that's the actual number. But it's 1024. You can just remember that number. So then we have a gigabyte. So a gigabyte is 1024 megabytes. Okay, and then we have one level above that. So what's bigger than a gigabyte? So we have a terabyte. So a terabyte, I should write this a little bit bigger, huh? A terabyte is 1024 gigabytes. And what do we have up from a terabyte? Petabyte. So a petabyte is 1024 terabytes. And what's up from a petabyte? I think it's a Z. I'm going to have to look it up. Hey.
I think it is
Zettabyte.
I think it is.
Make it up now. 1024 petabytes.
Is there even a petabyte or zettabyte servers?
Yes, definitely. Yeah, petabyte's not that big.
Like the Google servers, like.
Yeah, you think the amount of data stored on YouTube would be in the zettabyte range, you know? They'd have servers that would store. You think of the entire collection of YouTube videos. Alright, so we've started at the lowest level, which is the bit, and we've worked all the way up to the zettabyte. Right, now let's understand how these ones and zeros, you know, how we can use those to represent the numbers from, you know, 0 up to whatever we want to store in our computer. Is that okay with everybody so far? Okay. So, let's do the first thing, which is called binary counting. And this is just to show how these numbers, these ones and zeros, can be used to represent the digits that we're familiar with. 0. So, if we start at 0 and we want to try and represent these using our on and off switches, right? So 0, you can represent 0 just using one switch. Okay? And 0 basically means you just switch the switch off. So for now on, I'm going to use 0 to mean off and 1 to mean on for the switch. So 0 in decimal is 0 in binary. 1 in decimal is 1 in binary. So now, what have we done here? Let's see if we can apply the same rule here, you know? We went all the way up as far as 9 here, and then we used this positional thing that we've decided we're going to use to basically move the 1 over here and start again counting from 0. So we used to apply the same rule here as well. So we got 0 and 1, so what do we do when we run out of digits?
0, 0.
Yeah, we put a 1 over here and we start counting again. Same as we did here. We got to 9 and then we did 10. So the same thing here. If we only have 2 digits, then, you know, as soon as I run out of zeros and ones, I have to then use my positional system, the same positional system that we've done here. So, 3 is the sequence 1 and 1. And now we've run out of digits again. So we do the next thing. So we end up with 1, 0, 0. 5 is going to be 1, 0, 1, because I'm just counting again. You know, the same rule that I used to count in decimal, I'm going to use this rule here to count in my binary system. So 6 is going to be the number 1, 1, 0. 7 is going to be 1, 1, 1. And then 8 is going to be the number 1, 0, 0, 0. 9 will be the number 1, 0, 0, 1. And then 10 will be the number 1, 0, 1, 0. Okay, I think for a small exercise, will you guys try yourselves and figure out the numbers from 11 till 20 in binary? Just by using binary counting like that. Just use the exact same rule. When you run out of digits, you just shift 1 over to the left and you start counting again. You only have 1s and 0s. So, 11. 11 is going to be 1, 0, 1, 1. So I just go from 0 to 1. Alright? And then I see that I've run out of digits here, so the next one is going to be 1, 1, 0, 0. So 12 will be 1, 1, 0, 0. 13 will be 1, 1, 0, 1. 14 will be 1, 1, 1, 0. 15 will be 1, 1, 1, 1. And then 16 will be, because we've run out of digits now again, so the next thing happens, we stick in our zeros here. 17 will be 1, 0, 0, 0, 1. 18 will be 1, 0, 0, 1, 0. 19 will be 1, 0, 0, 1, 1. And then finally, 20 will be 1, 0, 1, 0, 0. I think.
Yeah.
Can you just double check that everyone get that? So if you didn't get exactly that, then it's okay. You can do the next 10 numbers by yourself, right, just for some practice. But you just have to, always the thing to do is to, when you're trying to work these number things back, is just work back to how you would do it in decimal numbers. You know, the basic principle is that you use up all your symbols. When you use up all your symbols, the 1 just gets bumped off to the left, and then you start at 0 again. So that's the rule for binary counting, and it's the same rule for decimal counting, but now we have 3 symbols. The number of symbols that you have is called the number base, alright? So the number base that we use for this decimal system is base 10, because we've got 10 symbols. We've got the symbols from 0 up to 9. This system here, which is the system that computers use, is called binary or base 2 numbers, because there's 2 symbols. There's just a 0 symbol and a 1 symbol. Alright, is everyone okay with binary counting? A little bit more practice, I'd say, with binary counting, and you'll be grand at it. Maybe make a game about it, and then you'll be good. Alright, so, some other things, some interesting things that we can see from looking at this sequence of numbers here, right? 0 and 1 are the same, that's interesting. But there's a few interesting numbers here which are interesting to observe. I think 7 and 8 are kind of interesting numbers, aren't they? Because 7 is all ones, and then 8 is like 1,000. It's kind of curious, isn't it? And then there's another interesting pattern that comes here at 15 and 16. You see, this is all ones, and then this is 1 followed by all the zeros. So, interestingly, oh, actually 3 and 4 are kind of interesting as well, because they have that same pattern, don't they? All the ones followed by 1, 0, 0. Can you see that pattern? So we find that pattern emerging at every time we have a power of 2. So 4 is a power of 2, 8 is a power of 2, 16 is a power of 2. By the way, what does that mean, a power of 2?
The 2 to the power of something would be that.
Let me just explain what power means, yeah. So, if you take 2 to the power of 2, that means 2 multiplied by 2, which is equals to 4. Alright, that's what to the power of means. If you have 2 to the power of 3, that's the same as 2 multiplied by 2 multiplied by 2, which is equals to 8. And then 2 to the power of 4 is equals to 2 multiplied by 2 multiplied by 2 multiplied by 2, which is equals to 16. And then 2 to the power of 5 is just 2 multiplied by itself 5 times, which will be equal to 32. So we just take the previous number multiplied by 2 and we get the power of. Interestingly, the same thing applies for base 10 numbers as well. If you take 10 to the power of 2, that's equals to 10 multiplied by 10, which is equals to 100. If you take 10 multiplied by 3, that's equals to 10 multiplied by 10 multiplied by 10, which is equals to 1,000. So you see the same thing applies. That's what to the power of. It just means the number is multiplied by itself a certain number of times. So to the power of 3 means it's multiplied by itself 3 times. Okay, so that's what to the power of means, right? And rather curiously, these numbers, 8 is a power of 2, isn't it? 16 is also a power of 2, and this is also a power of 2. So these numbers, where we see these patterns in this table here, are power of 2 numbers. So the power of 2 is an important kind of concept to understand. And to understand the relationship between these numbers, we can see that the power of 2 is kind of important here, isn't it? It's important in the generation of this pattern. Interestingly, 10 to the power of 1 is equals to what? It's just equals to 10. Okay? And what about 10 to the power of 0? What's that equal to? So, okay.
So it's always equal to 1.
Yeah, anything to the power of 1, the rule is always equals to 1. So anything to the power of 0 is always equals to 1. Anything to the power of 1 is always equals to itself. So over here, 2 to the power of 1 would be equals to 2. 2 to the power of 0 would be equal to 1. Okay, so anything to the power of 0 is always equals to 1. Maybe write a note there, just for your own memory. Okay, an interesting thing to observe. Let's go back to our decimal numbers. If you remember when we started this discussion, we started looking at the decimal number system and the positioning of the digits and stuff like that. Let's go back and let's pick this number 127. We said that 7, this is the ones column. Did we say that? This is going to be the tens column, and this is the hundredths column. Alright? Notice that these are all powers of 10. 10. So this number here, the ones column, this is 10 to the power of 0. This is 10 to the power of 1, and this is 10 to the power of 2. You see that? So the columns determine, you know, what power of 10 we're using, or what power of 10 the number in the column signifies. Do you see that, everybody? The same thing applies for binary numbers as well. So if I pick, let's say, this binary number for 13 here, and I pick the number 1101, which is the number 13, well, these correspond to powers of 2. So this is the 2 to the power of 0 column, this is the 2 to the 1 column, the 2 to the 2 column, and the 2 to the 4 column. So therefore, 2 to the 1 we said was, sorry, 2 to the 0 is 1, 2 to the 2 is 2, 2 to the 2 is 4, and 2 to the 4 is 8. And when we add up 8 plus 4, we get 12, plus 1 is 13. So that's how you convert between a number in the base 2 system to a number in the base 10 system. Everybody see that? Okay, so you just write above each column what the column represents, okay, and it's always a power of 2, starting at 0 from the right to the left. Same as the decimal number system, powers of 2, sorry, powers of 10, 10 to the 0, 10 to the 1, 10 to the 2 column. Okay, in the binary number system, 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 4. So it's the same sequence, apart from we use 2 instead of 10. And using this approach, we can convert numbers from binary to the decimal number system. So you just write above each column what the column represents, and then you sum up all the numbers. Yeah.
Why do you ignore the 2? Like, instead of skip over it?
Oh, because it's 0. So this means 0 multiplied by 2, 1 multiplied by 1, 1 multiplied by 4, 1 multiplied by 8. In the same way here, this is 7 multiplied by 1, 2 multiplied by 10, and 1 multiplied by 100. Sorry, maybe I didn't.
No. It was,
Good question, good question. If I didn't explain that. Okay, time for an exercise. I'm going to give you a string of binary numbers, and I want you to tell me what does this represent as a decimal number. Okay, here's the string of binary numbers. 1, 0, 1, 1. Let's try that one. Did we do that one? Ah. 1, 0, 1, 1, 1. There's a string of binary numbers. I'll do a second one, right? Try 0, 1, 1, 0, 1. There's 2 examples. Try and convert those to the decimal equivalent and try and figure out what those sequences of binary numbers represents in decimal, okay? So the trick to do this is to write above each column what the number is going to be multiplied by, and it will be a power of 2, starting at, 0, 1, 2, 3, 4. Right up, let's do the first sequence of numbers. 1, 0, 1, 1, 1. Okay, we'll do the first one. So again, we just remember that this is the 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and 2 to the 4 column. And if you're not sure why that is, then look back at decimal numbers, because decimal numbers, it's exactly the same thing. 10 to the 1, 10 to the 2, 10 to the 3 column. 2 to the 0 is going to be 1. 2 to the 1 is going to be 2. 2 to the 2 will be 4. This will be the 8th column, and this will be the 16th column. So we have a 1 here, so that's 1. We have 2 to the 2, which is going to be 2. So that will be 1 and 2, 1 plus 2. We have another 4 in this column here, and then we've got a 16 in this column here. Is that okay with everybody? So it'll be 16 and 4 is 20, plus 2 is 22, and 1 is 23. Okay with everybody? Did I make any mistakes? It's okay, good. You're QAing my calculations here, because it's very easy to make mistakes when we're doing these calculations by hand. So then we have 1, 0, 1, 1, and then a 0. 1, 0, 1, 1, and a 0. So for this number, we've got 2 plus 4 plus 8, which is...
It's 1 plus... first one.
Sorry, 1 plus 4 is 5 plus 8 is 13 for that number. Is that okay with everybody? And then we'll try the third one here. This one we'll try just doing in our heads maybe. So this is going to be the 1 plus 4 is 5. Ah, here, I can't do it in my head.
Getting really big.
1, 0, 1, 0, 1, 1, 0, and 1. So we'll put these columns in here as well. This is going to be the 32 column, 64 column, and the 128 column. So this will be 1 plus 4 plus 16 plus 32 plus 128. Is that right?
Yep.
Cool. So 128 is 130, 150, 166, 170.
180.
Okay. 82, sorry. 128 plus 32. Oh yeah, that's 160, isn't it?
Yeah.
Not 150. So 160, 176, 180, and then 181. I forgot the one here. Thank you. 181. Okay. So we now know how to convert binary numbers to decimal numbers. The thing that's worth maybe considering at this point is like going back to our original question. It's like, what does an 8-bit aesthetic, a 16-bit aesthetic mean, right? Let's see how many colors or how many combinations we could represent in numbers of bits, right? Let's say I just have a single bit. That's all I have. How many different combinations do we have? 2, because the bit can be either on or off. Right, so there's only 2 combinations. If I have 2 bits, how many combinations do I have? I have 4 combinations, right? Let's write them out. So both switches could be off. This switch could be off and the other one could be on. This switch could be off and the other one could be on. Or they both could be on. So we've now iterated through all the possible combinations of the switches, and we've discovered that with 2 switches, we have 4 combinations. All right. Let's say we add an extra switch. If we have 3 switches, how many combinations do we have? So we can start with them all off and then gradually turn them all on until we have realized that we've gone through every possible combination of on and off switches. One, 1. So we discover with 3 switches, if we turn them all on and off and we go through every possible combination of the switches, we discover that we have 8 combinations. Can you see that? If we have 4 switches, how many combinations will we have? 16, exactly. So by adding an extra switch, we double the number of possible combinations of switches that we can arrange. Does everybody see that? So, interestingly, when we talk about an 8-bit aesthetic, an 8-bit aesthetic generally uses 16 colors, right? 16 colors. And that's what an 8-bit aesthetic typically means. And the reason why is because on 8-bit computers like the Commodore 64 and the Sinclair Spectrum, each nibble was used to represent the color of a single pixel on the screen. So if you have a nibble, you basically have 4 bits, which means you've got 16 possible colors that you can represent if you have 4 bits. Nowadays, we use either 24-bit or 32-bit colors to represent our colors, right? So with 24-bit, how many possible combinations do we have? Well, we have lots of combinations. But with 24 bits, what do we have? We basically have 3 8-bit combinations. If we have a single 8-bit number, how many combinations do we have? This is a number that you should maybe know or be familiar with.
256.
You have 256 different combinations, right? So if you combine 3 of those together into 24 bits, the way it's typically used is you have one 8-bit number for red. So you've got 0 to 256 for the red component. You have one 8-bit for the green component. So you've got 256 combinations. And then you also have one 8-bit number for the blue component. And so you have another 256 combinations together there. And as you know, you can make any color that can be perceived by the human eye by combining red, green and blue together. And a 24-bit number is enough to represent the entire colour palette that the human eye can recognise by combining red, green and blue. So why do we bother with 32-bit numbers then, or 32-bit colours? Yeah, so you add alpha, you know, red, green, blue, and then the final 8 bits is used to denote the alpha channel, or how transparent that pixel is going to be relative to what it's been drawn on top of. So that's RGB alpha, and that's why we use 32-bit numbers. People often talk about 16-bit games. So what type of computers were 16-bit computers? Actually, let's make a note on that. It's kind of interesting to... The 8-bit era. The 8-bit era. The 8-bit era. What type of computers would we have used in the 8-bit era?
Spectrum.
Yeah, I'm not too sure about consoles now, but I'll take your word for that, yeah? Make sense.
The master system was 8-bit and then the Genesis
Maybe. I would think maybe sort of something like the Atari 2600 was definitely an 8-bit one, you know? Commodore 64, stuff like the C64, Spectrum,
Amstrad.
yeah, Amstrad, all of those ones.
MSX.
Yeah, MSX was just what I had. Great machines. I still have one actually. I bought an MSX2 on eBay there last year. So I can play my MSX games on floppy disk. Yeah, but I originally would have played them on tape. So there's the Spectrum, the Amstrad, the MSX, all of those stuff. 16-bit era computers. Again, I'm not too sure about consoles. I'd actually probably have to look it up, but I guess, you know, you look up the consoles. I know there was 2 big computers of what we call the 16-bit era.
The 286.
What? Yeah, the Atari ST and the Amiga. And then the 32-bit era would be stuff like the PC and things like that would be 32-bit. And now, of course, all computers have 64-bit CPUs. A 64-bit CPU versus an 8-bit CPU just determines the amount of the size of what are called the registers inside the CPU, but it also determines how much information can be processed in one instruction. So for an 8-bit computer, it basically had to process or load in 8 bits of information, do some calculation, send the 8 bits back out again. At 16 bits, you could take in twice as much information, do a much bigger calculation on a much bigger number, and then so on up as far as 64-bit numbers. How do we do for time? Well, it's time for a short break. Let's take a 10-minute break, and we'll come back and maybe try and write some processing code to explore these numbers in a little bit more detail, okay? That they should be healthy and walk instead. Okay, so just to recap about what would be good to know from that first class that we had. So it'd be good to know about base 10 and base 2 number systems. It'd be good to know what all of those terms means, like gigabytes, megabytes, all that kind of stuff. It'd be good to know how to convert from a decimal number to a binary number. That's a useful thing to know. How you go from a binary number to a decimal number. How you go the other way is kind of interesting, and there's a little trick that you can use. And we might try to write some processing code to do this, but I'll show you the technique first of all. Let's say you pick the number 58, and I want to figure out what is the binary sequence that represents the number 58. So the technique we use is called the divide by 2 technique. And what you do for the divide by 2 technique is you divide 58 by 2. So 58 divided by 2 would be 25, and 8 divided by 2 is 4, so 29. Yeah? So 29 is 58 divided by 2. And there's no remainder, so we put a 0 up there. So the remainder, remember, the remainder is what's left over when you divide one number into another number. Alright, so you take 58 divided by 2 gives you 29. And then we divide this number into by 2 as well. So 29 divided by 2 is 14, isn't it? 14.5, or 14 with a remainder of 1. Okay? 2 into 14 goes 7 times with a remainder of 0. 2 into 7 is 3 times with the remainder of 1. Yeah, 2 into 3 goes 1 time with the remainder of 1. 2 into 1 is 0 times with the remainder of 1. So by looking at the remainders here, you reading from the bottom up, you end up with the binary sequence which represents 58. So the binary sequence that represents 58 is 1, 1, 1, 0, 1, 0. And we can work backwards to make sure that this is in fact a binary sequence, right? So the binary sequence, this is 1, well, this will be 2, 4, 8, 16, 32. So 32 plus 16 is 48, plus 8 is 56, plus 2 is 58. So when you go backwards, you realize, you can verify that the number is actually correct. So that's the number 58. Alright, so just to be clear again, you start with your number, divide by 2, you put the remainder over here, and then you divide that by 2, and you keep on going until you end up with 0 here. Interestingly, you can keep going from this point here, and it doesn't make any difference. You just keep on playing. But it makes sense to stop at 0. 2 into 0 goes how many times? Goes 0 times, and what's the remainder? 0. So you can put another 0 over here if you really want it, and you can continue to put zeros here. And it doesn't affect the value of the number. Same as if you did it in decimal. If you take the number 56 and you put a 0 in front of the 56, it doesn't affect the 56. Of course, if you put the 0 on this side, it changes 56 into 560. So the same thing applies in the decimal system as well. If you put numbers off to the left and it doesn't affect the value, put numbers to the right and it does affect the value. So I'll do one more example of this, and then I'll get you guys to try one yourselves, right? Let's pick... That's okay. We'll do another one, right? Pick the number. Hey!
How was the elevator?
Elevators.
I almost cried.
We know.
There was like 4 socials.
Your friend is uplifting.
Maybe you got the one in the elevator.
Okay, now, for those who came late, we just did this little calculation here, which is to go the other way around, to change a decimal number into a binary number. You start with the decimal number over here, and you divide by 2. So 2 into 25 is 12, and a remainder of 1. Okay? And then you go 2 into 12 goes 6 times, and a remainder of 0. 2 into 6 is 3 with a remainder of 0. 2 into 3 is 1 with a remainder of 1. 2 into 1 goes 0 times with a remainder of 1. And you can stop then once you get a 0 at the bottom. And then you read from the bottom up, and that's your binary number. So we end up with the number 1, 1, 0, 0, 1. And just to verify that that's the correct number, that's 1, 2, 4, 8, and 16. So 16 plus 8 is 24, plus 1 is 25. Alright, so I'll give you guys a number and you can tell me what it is in binary using this technique, right? So let's take the number 77 and convert that one to binary using that technique. Okay? Just try yourselves. Okay, everybody, let's try this one. Okay, everybody, let's try this one. Okay, let's pick the number 77. So 77 divided by 2 is going to be 38. Remainder 1. And then 2 into 38 would be 19. Oh yeah. Remainder 0. 2 into 19 would be 2 9s are 18, so 9 remainder 1. 2 into 9 is 4 times remainder 1. 2 into 4 goes twice, remainder 0. 2 into 2 goes once, remainder 0. And 2 into 1 goes 0 times remainder 1. So reading from the bottom up,
1 1 0 0 1 1 0
1 0 0 1 1 0 1. So that's 1, 2, 4, 8, 16, 32, 64. 64 plus 8 is 72, plus 4 is 76, plus 1 is 77. Figured it out. Is that okay with everybody? Now, that's a simple little technique, right? It's probably very rare that you'd ever have to, you know, take a decimal number and convert it into a binary number. It does come up that you have to deal with binary numbers occasionally. For example, you know, maybe, I don't know, in games if there's a huge example of it, but certainly in computer science, if you're doing anything to do with configuring routers or anything like that, you know, you're used to dealing with IP addresses. IP addresses are how many bits? Would you have an idea? Okay, so give me an example of an IP address. Anyone?
192.168.1.1.
Okay, so that's an IP address. Is this a valid IP address? 267.12.-1.17.
The maximum is.
Okay, so number one, no negative values. What's the other problem with that one?
The last
The maximum number is 255.
Maximum number is 255. Yeah, so 0 to 255. And that's because each bit of this here, or each bit is the wrong term, each component of this IP address corresponds to 8 bits. And that's why the number can only be between 0 and 255. Because there's 256 different combinations, we realize, with 2 to the power of 8. So each bit of this, or each component of this IP address corresponds to 8 bits out of 8, 8, 8, and 8. So in total we have 32. So an IP address is a 32-bit number, which actually is an interesting fact. How many unique IP addresses are there?
There's 2 types. There's
IPv4
and IPv6.
Sure, IPv4 IP
There's a
addresses.
new one coming out as well. So I don't know the exact.
So say IPv4. These are IPv4 addresses. So there's 2 to the power of 32. A very significant number. And it actually is a very significant number, not just for IP addresses, but also for operating systems as well. When we talk about Windows 32 and Windows 64, what's the maximum amount of addressable RAM in a Windows 32 computer? 4 GB. So 4 GB is roughly 4 billion. And that also is, you know, 32. This is where there's 4 billion unique IP addresses. And that's why we're always running out of IP addresses. Because there's obviously many people on the planet, 6 billion people. Almost everybody's got a mobile phone. They can't all have a unique IP address. And then there's all the other connected devices that are connected to the internet. Laptops, computers, servers, Arduinos. So there's a shortage of IP addresses. There aren't enough IP addresses for everything on the planet to get its own IP address. You know what an IP address is, don't you? If you've ever set up a server, you know, a Minecraft server or anything like that, you'll be dealing with IP addresses. Every computer connected to the internet has its own unique number called its IP address. And on a network, every computer has its own unique one. So there's various techniques for getting around this limitation. So for example, on a subnet, which is for example the DIT, you guys don't have public IP addresses. You guys have an IP address which is just unique to the network that you're currently connected to. You know, but maybe there's only one IP address for the whole of DIT that you guys are all sharing, the public IP address. You know, there's various things called port mapping and stuff like that. You can get around this limitation of only having 4 billion. The new system for this is called IPv6. IPv6 uses 128-bit IP addresses. So you have 2 to the power of 128, which is an absolutely humongous number. It's more than, I think, there are atoms of hydrogen in the known universe, or some ridiculously huge number. In other words, there's enough for every doorknob, for every brick on the planet to have its own unique IP address in the IPv6 system. We will need that. Well, we absolutely will. When you think about all the smart devices that we are acquiring, even now there aren't enough IP addresses. But you know, go forward 10, 15 years when we're all carrying around smart keys and smart glasses and smart jackets and smart whatevers. We will need more IP addresses. Okay. Right, the last thing we'll do today then, okay, to relate all of this to programming. We don't have enough time to do this, but it's an interesting exercise, right? First of all, let's talk about how all of this stuff relates to programming. There are various what we call data types in processing. We're used to declaring variables of different types. So first of all, we have this type called a car. So how big is a car in processing? How many bits?
1 bit.
16.
So a car is a single character from a string. Huh? Well, think about it. How many letters of the alphabet are there? There's 26 letters of the alphabet. Plus you have all of the keys on the keyboard, all of the characters in all the other alphabets in the word. So a character can't be the single bit, because then we could only have the character of 0 or 1.
I'm guessing 256.
Okay, 256 bits is how a character used to be stored, and in languages like C, it's a 8 bits. 8 bits, not 256 bits, which means you got 256 combinations. Characters used to use an encoding system called ASCII, which was an 8-bit system, right? In fact, a 7-bit system, but expanded to 8. Nowadays, characters use a system called Unicode. And Unicode is a 16-bit system, or a 32-bit system. But anyway, that's the size of a character. I think it's a 16-bit. You can do size on or something in Java or processing to figure out exactly how big it is. It's 16 bits minimum. What?
Isn't Unicode like for emojis and all that as well?
Yeah, Unicode is everything, including stuff like the, OGM system for things that every character in. There's a Unicode consortium which decides which characters become part of Unicode. Yeah. So that's a character. What about an integer? How many bits does an integer take up?
Is it 22,000?
It's, well, bits now,
Oh,
bits.
bits.
Yeah. Or how many bytes are bits?
2 bytes.
2 bytes.
No, 1 byte is
It's 32 bits, so it's 4 bytes. In Java, an integer is 4 bytes. And in Unity, that's the case as well. So it's 4 bytes. So you basically have 2 to the power of 32 combinations for integers. A float. 64 bit. Okay, anyone like to have any guess? How many bytes or bits? That's 32 bits. 8 bytes, we think. The answer is... The answer is 4 bytes. Same size as an integer. So floats and integers take up the same amount of memory in your computer, but how is it possible that a float can store stuff after the decimal point and an integer can't? The answer is that floats actually use a completely different system. They use binary, but they don't use the same system as integers. They use a system, which I won't teach you. It's a very computer science thing. And it'd be pointless for you to learn. I can't imagine you'd ever have a use for knowing how floating point numbers are stored. As game designers, it's just not the sort of stuff that comes up in game design meetings, I think. It uses a system called, but here, again, on your first date, you want to try and have a good conversation starter, right? IEEE 754 floating point format is how it's actually stored, and it uses exponents and things like that. So to make the decimal point float along the 32 bits. That's kind of how it works. That's why they're called floating point numbers. Then we have this thing called a double. And a double is 8 bytes. Some languages, and I don't know, I think Java has them, longs. Longs are also 8 bytes. They're just basically big integers. Like an integer, but it can just store 8 bytes worth of an integer instead of 16 or 32 bytes worth of an integer.
How do you get away with it in Java?
I can't remember, in most languages like C and C++ and all, there's a thing called a log. I can't remember if they're in Java or not, off the top of my head. And I program in so many different languages, I'm not really too sure. Anyway, that's the size. What about something like a Boolean?
That would be
Two.
on or off.
So we think a single bit can be used to store a Boolean. But if you remember at the start, I said the smallest amount of addressable memory in a computer is usually a byte. So the minimum that can be used to store a Boolean is an actual byte. So a whole 8 bits, so there's 7 bits wasted in a Boolean. I think it's 1 byte.
Why would it be
So-
wasted?
What's that?
Why would it be